All right, so let's look at the experiment number 1. So as usual, we'll use circuit simulation as a tool to understand and design circuits. So our lab number 7, it revolves around bipolar junction transistor. So the first thing we'll do is study the characteristics of bipolar transistor. And then we will use this particular bipolar transistor, make an amplifier and study its characteristics. And then we'll make a inverter, a gate, a simple NOT gate, and we'll study the properties of that particular NOT gate, and then use a similar approach to design NOR, 2-input NOR and 2-input NAND gates, and we'll study the behavior of these two logic gates as well. All right, so let's open up the simulator and look at the details of what we have to do. So this is the bipolar transistor here, and we'll use a bipolar transistor called BC547. And to study the properties, what we'll do is connect a current source initially to the base and apply a voltage at the collector, right? So all of you may remember, to turn the transistor on, you have to bias the base. You have to base current should be greater than 0. Base current in an NPN transistor should flow into the base here. And we also need a voltage across the collector emitter voltage here. So in the present case, I've put a base current of 10 microamperes, as you can see here. So let me put here 10 microamperes of base current, and we can do dynamic simulation, dynamic DC, and look at the current here, right? So we see, of course, we have applied a voltage of 2 volt. So let's enable this 2 volts here, and 2 volts is applied, and we have a voltage of, this is the base voltage here. So between base and emitter, if you recall, there is a diode here, and we have a voltage of 0.682 volts here, right? So it's close to 0.7 volts that many times we expect from a diode here. And let's look at the current flowing here. So we have 10 microamperes base current, and we have a current of 4.399, so almost 4.4 milliamperes flowing in from the collector here. So the gain of the current gain of the transistor would be 4.3 or 4.4 milliamperes divided by 10 microamperes here. So almost like 440 is the kind of current gain here. All right, so let's explore this characteristics further. By the way, the bipolar transistor that you see here, there is a base, emitter, and collector, of course. It's not a symmetrical device. So for example, in this case, as you can see clearly, as we saw, if the base current is 10 microamperes, the collector current is 4.39. So the current gain is 440. Now what we can do is, you know that we call it NPN transistor. So both emitter and collector are N-type, but we can't simply interchange it. So let me actually do it. So, right, so let me interchange the emitter and collector here, right? So now look at the gain of the transistor here. So as usual, base current is 10 microamperes, but the collector current now, or the when you interchange emitter and collector, the current that is coming in here is 24.386 microamperes. So the gain here is only 2.4. So the transistor is asymmetrical, and if you interchange emitter and collector, then you don't get enough gain here. So you have to be careful when you're using a transistor. You have to make sure that you're using the proper terminals when you make the circuit here. All right, so anyway, so that's a transistor operated in reverse direction here. So let's put it back to is the normal mode here. Okay, so what we can do is study the characteristics of this particular transistor in more detail. For example, we can do, so let's come out of dynamic DC, we can do a DC analysis. And in DC analysis, what we are going to do is, we'll put in a base current, and we want to see how the collector current changes with collector emitter voltage here, right? So let's do that. So I'm going to sweep collector emitter voltage from 2 volt to 0 volt at intervals of 0.02, and I'm going to look at the collector current of transistor Q1. Okay, and as usual, we have auto scale here. So let's run it here. Right, so in addition, what I did was, what you can do here is you can step, there's something called stepping. So what I did was, I stepped the base current. So you can simulate it for different values of base current. So I stepped the base current from 20 microamperes to 80 microamperes with a step of 20 microamperes. So we'll get a family of curves. First one at 20 microamperes, then the next one at 40 and 60 and 80. So we'll get 4 curves here. And that's what we are getting here. 4 curves here, you can see 20, this for 20, this for 40 and 60 and 80. So we get a family of curves. Each curve that you see here is for a fixed value of base current here. All right. So we can clearly see 2 distinct regions. There's a region here where the current is almost constant. And there's a current here where the current is rapidly dropping with the reduction in the value of the collector emitter voltage here. So this is the region, we call it as the forward active region here, forward active region of the transistor. And in this region, note the characteristics here. We are talking about collector current versus collector emitter voltage here. So we're talking about the output characteristics here. And in this region, if we look at this particular region, the collector current doesn't depend much on the collector emitter voltage. So the transistor from the output side looks like a current source here, because there's a current flowing and the current doesn't depend on the voltage across it, right? As we change the voltage, the current is not sensitive to it. So it acts like a current source here. But this current source depends on the values of the base current. There's one value of base current here, another value here, and another value here. So it's a current control current source here. So by applying different values of the base current, we are getting different values of collector current here. So the transistor is acting as a current controlled current source here. And it is this property here, current control current source. And by the way, as you're changing the base current, the other way of doing this would have been, for example, we could have changed the base emitter voltage here. And as you change the base emitter voltage, the base current changes and you would get a similar characteristics. So you can look upon bipolar transistor also as a voltage control current source here, right? So voltage control current source or a current control current source, both of them you can look upon bipolar transistor as behaving in that particular manner here. And this is a region which we exploit in order to construct an amplifier. If you take a transistor, bias it in this particular region, and then you apply a small signal, you would see amplification occurring if you bias it properly here. All right, so that's your bipolar transistor. Its output characteristics. If you wish, you can look at how the base current, how the base current and the base emitter voltage change with respect to each other. And that is something that we know, that between base and emitter is a diode. So you would see that the base current and base emitter voltage, they change in an exponential manner. So it's basically a diode here. All right, so that's, but you can explore. You can see how IB versus VB change. You can also look at how IC, the collector current, changes as a function of base emitter voltage here. So even that, for example, you could explore. So the transistor characteristics you can explore and see how it behaves here. This region where the current is dropping with collector emitter voltage, this is the region we call as the saturation region here. So in this region, you can, for example, this region is occurring at, let's say, the collector emitter voltage is approximately, let's say, 0.1 volt here. So in this particular region, when you have 0.1 volt voltage applied, you would see that both the transistors are, both the junctions, there's a base emitter junction and there's a base collector junction, both of them are forward biased here. And for example, we could study that by, let's say, changing it to 0.1 volt, right? So let's do that 0.1 volt and let's do dynamic DC here. So note that the voltage at the base is 653 millivolt here, but the voltage at the collector is 100 millivolts. So this junction here, there's a voltage across the base collector junction also. So it's also forward biased. And if we look at the current here, So current, of course, is 10 microamperes. There's 1.53, there's 1.543 here. And note that because the transistor is in saturation region, if you look at the ratio of 1.543 and 10, right? So you don't have a gain of 440 that we had here. You have a gain which is much smaller here. So one of the characteristics is that when a transistor goes into saturation region, its current gain becomes smaller. So it will become even smaller if we go to, let's say, even deeper into saturation region, 0.05. So note that when I apply 0.05, the current here is 302 microamperes. So 302 divided by 10, so the current gain is only 30. So the current gain has dropped, right? So, but this is a region which we will use when we use a transistor as a switch. But for a transistor as an amplifier, we would like to bias it in the active mode here, forward active mode. So we apply a larger voltage here, 2 volt, and then we get back our characteristics here. All right, so all of these things you can explore by varying the base currents, by applying, or you can remove the base current, you can apply a voltage here, and thereby you can get the characteristics as a function of the voltage here. So all of those things that you can explore to understand this particular transistor properly here. Back to if you're for example, let's go back to our DC characteristics, and it appears as if it is constant, but there would be a slope here. For example, if we zoom here, it's not exactly constant, but you can see further zooming that there's a slope here, right? So the current is not exactly constant, but the current does depend on a collector emitter voltage here, and that can be of importance in many circuits that are there here. Anyway, so all of those things, as we are saying, you can explore. You have the tool before you, and you can use that to understand bipolar transistor properly here. The next thing is, let's look at the amplifier here. So this is the amplifier. Let's first of all remove all this. So this is the amplifier that we have constructed. So we have a bipolar transistor. We've used a base resistor here to bias the and the supply voltage, of course, to bias the transistor here. So remember, we have to supply a base current here. So the value of base current, VCC here and RB here, and there is a 0.7 volt, let's say approximately here. So we can easily calculate how much base current flows here. So that base current will cause a certain collector current to flow, and we put a resistor RC here to have a certain value of collector emitter voltage and to obtain a gain at this particular point here. So in red is all the biasing circuit. We have a supply voltage, we have a base resistor, we have a collector resistor. This is all the biasing arrangement for this particular transistor here. This is the part where we apply the signal that we want to amplify. So we've used a sinusoidal signal, and we are coupling it through a capacitor. So this is the signal that we're applying, and this is the place where we are taking the output. All right. Our interest is in the sinusoidal or the signal here. So we use a capacitor to block any DC and obtain the sinusoidal signal here. So if you go back to your notes of ESC201, you would see that an amplifier like this has a gain which can be expressed as GM, transconductance of the bipolar transistor, multiplied by RC here. Multiplied by RC, and actually RC in parallel with RL here. So the load resistor will come in parallel with RL here. So this expression is correct if the load resistor is very, very large. But you need to correct this. It would be GM RC parallel RL here in parallel. So when you draw the AC equivalent circuit, RC will come in parallel with RL. The capacitors would act like a short, and RC will come out to be in parallel here, right? So that's GM RC parallel RL, and the GM of the transistor depends on the biasing current. So GM is equal to the DC current flowing through the transistor divided by the thermal voltage, which is 26 millivolt here. All right, so that is that's there. And so the first thing, when you make an amplifier, you can check the biasing condition here. So for example, we can do again dynamic DC, and it will tell us how the transistor is biased here. So we can see that there is a 682 millivolt here, we can check, and the collector voltage here, collector emitter voltage is about 4.5 volt here. So it's roughly biased in the middle here. We have a 9 volt supply from the top here to the ground, and the collector emitter voltage is around 4.5. The remaining voltage is dropping across RC here. You can see the currents that are going in here. So we have a base current of 10 microamperes. That's where we have biased it. And we have a collector current of 4.5 milliamperes here. Now you can obviously change the biasing current. You can change the base current by changing the value of the voltage here. You can also change the voltage across the collector emitter voltage by changing the value of RC here. Right? So these are the things that you can use to alter the biasing of this particular transistor here, of this particular amplifier here. So the next thing is we have applied you can see here, we have applied a sinusoidal voltage 10 millivolt frequency of 1 kilohertz here. And we can see now, and the output is being taken at this cross here, across the voltage at this particular point. So there are two ways we can analyze this particular amplifier. One is, normally we do small signal or AC analysis, in which the transistor is considered as a linear element. And for that, we can do a AC analysis here. So AC analysis will, use a small signal model for a transistor here. And in AC analysis, the entire circuit is linear. So what is of interest is what is the ratio of V out by V in the gain here. So let's do the AC analysis here. All right, so in AC analysis, I am sweeping the frequency from a fairly high value from 1 gigahertz to 1 hertz here, because I want to look at the variation of gain with frequency. And I'm looking at the magnitude of V out plotted in terms of dB here. You can also look at simply the magnitude of the output voltage. That also is possible. But in this case, I want to look at dB, because I also want to look at the 3 dB frequency here. If you want, you can look at the phase also. So, but right now, let me remove the phase part here. You can explore how the phase of the output voltage also changes here. And all right, so we have everything before us. So let's run the simulation. Okay, so that's a typical variation that you see here. Right, so let me put it so that we can see the schematic also. All right, so that's our amplifier, and this is the result that we get here. So two things we see here. The first one is there's a range where the gain is independent of frequency. So this is what we call as the mid-band frequency region here. And this is the useful region for transistor or for amplifier operation here. Why? Because we don't want amplifier to amplify different frequencies select in a different manner here. Whatever is the nature of the input, we would like the amplifier to preserve that nature. If there is a component at 100 hertz and there's a component at 1 kilohertz, and the 1 kilohertz component is higher in magnitude than 100 hertz, we would like that kind of a relationship to be preserved. We want the entire thing to be magnified, but the relationships among different frequencies, we would like to preserve that. So that would happen in this particular region here, right? So this is where the gain is independent of frequency. But in an amplifier like this, the gain is falling or becoming frequency dependent here. So this is the low frequency region here. So in the low frequency region, what happens is these capacitors that you see here, which we thought as shorts, they're no longer shorts. And therefore, they begin to affect the transistor characteristics, this capacitor here and this capacitor here. So they are causing a frequency dependent characteristics. Once the frequency goes above a certain limit here, these capacitors are practically shorts, and then the circuit becomes independent of frequency here. So this part, low frequency region, is being controlled by these two capacitors, and is always in RC time constant. So this capacitor and the resistance that this particular capacitor sees, and this capacitance and the resistor it sees, these are the ones that are controlling it here. Anyway, so this is the mid-band range here. At high frequencies, again, the gain falls here. And again, the gain falls here. Now, this comes about because there are capacitances that are internal to the transistor here. And unlike capacitors that you see here, which are in microfarads, the capacitors which are internal are in picofarads. or even smaller, or depending on the nature of the transistor here. So these capacitors begin to become important, and they pull the gain down here at higher frequencies here. So the useful range of amplifier operation is here. And basically you have to find out, for example, if I use, you can see here, so this is 37.144 is the mid-band gain here. And you can find out where the gain falls by 3 dB here. So that's called the lower cutoff frequency. And where the gain falls by 3 dB on the other side, that will be called the upper cutoff frequency. So between the upper cutoff frequency and the lower cutoff frequency, that is what we will call as the bandwidth of the amplifier here. So 37.144. So what we can do is we can go ahead and find a point which is 3 dB lower. So that should be 34.144. So let's find 34.144. So 34.144. So we can find tag left. All right, so let's, okay. All right, so let's go here first of all and go here again and tag left. So that's 34.144. And we want to do tag right here, let's see. Let's see if it does it. Tag right. All right, so, okay. And the frequency at this point is 90.794 megahertz. And the frequency on the left-hand side is 10.489 megahertz. The difference of the two is 90.79 megahertz here. So that's the bandwidth of the amplifier here. So our amplifier at present has a bandwidth of 90.8 megahertz is the bandwidth of this particular amplifier. So now what you could do is you could explore, for example, the gain and the bandwidth are related together here. So you could try and increase the gain of the amplifier. You could, for example, increase the gain of the amplifier by increasing the value of RC, or by increasing the value of GM. By reducing the value of RB, you can increase base current, and that would increase the collector current and the transconductance, and that would also increase the gain of the amplifier here. And you could try and alter the gain of the amplifier, and you can explore what happens to the bandwidth. So there's a well-known gain bandwidth product which says that as you try to increase the gain, the bandwidth will decrease. So you can explore all of that using this particular simulation here. Also, you can explore the phase part here. So I'll leave that for the moment here. So you can explore the phase part of this particular amplifier and look at the phase relationship between the output and the input. And you would see 180-degree phase shift in the mid-band range, but at lower frequencies and higher frequencies, you would see phase changing, departing from 180-degree phase shift here. So that's in the AC analysis you can use to explore how this particular amplifier works. The other thing that you can do is you can do a transient simulation. And transient simulation is the most accurate simulation, because AC simulation actually sort of linearizes the transistor and makes approximations in looking at how the transistor behaves. The transient simulation does not do any of that, and you can get an actual realistic picture of how the amplifier will, if you actually go and make the amplifier, how it will actually work here. So when we do transient simulation, so the signal is 10 millivolt, 1 kilohertz sinusoid. And we're going to look at the relationship between V out and V in here, right? So this is V in and V out here. So let's do transient. So in transient simulation, because our frequency is 1 kilohertz, so I'm going to run it for 2 milliseconds, so that at least I have 2 time periods. Maximum time step, you have to sufficiently, this is too high, so maybe I can even decrease it to 0.01. And I'm going to plot the input voltage and the output voltage. I want to see the relationship between them. So let's do that. Let's run, and operating point, auto scale, all of that is there. So let's run it. All right, so that's what we see. So in blue is the input here. Note that the scales are different. So we have applied 10 millivolt that you see here, right? And as we said, the output voltage. So if you're wondering where we are taking the output voltage here, So we can put the circuit like this here, so you can see, right? So this is where we are taking the output voltage here, and this is our plot here, right? So the output voltage is 180 degree out of phase with the input here. So that's what we were talking about. At 1 kilohertz, the capacitors are practically like shorts, and you see 180 degree phase shift here. Note that if I don't put a capacitor which is sufficiently large, suppose I just make it, just for the sake of argument, suppose I make it 10 nanofarad. Let's see how it changes here. So note that the relationship, you don't see 180 degree phase shift, and you see that the gain has collapsed. You look at the scale here, this is 150 millivolt is the kind of a scale that we see for the output here roughly, and input is still 10. So you don't have that much gain. You have a gain of only 15. And the relationship between input and output is also not 180 degree. And the basic reason is that the capacitor at that particular frequency, a lot of voltage that you apply, a lot of voltage is dropping across the capacitor here and is not going into the amplifier at that frequency at 1 kilohertz. You can calculate the impedance here, and you'll see the impedance is sufficiently high. So the capacitor doesn't act like a short here. But when I make it 10 micro, well, then you can see here. All right, so it goes back to 180 degree phase shift here. So it's almost like a short here, right? And now you can see how much is the gain here. So let's explore that further. And we will also see that even though the input you can see is a perfect sinusoid, one way of looking at the quality of a sinusoid is look at the positive amplitude and look at the negative amplitude here. So you see positive amplitude is 10 millivolt and negative amplitude is minus 10 millivolt, perfect sinusoid. All right, so let's look at the output here and see what happens here. So let's look at, let's use a cursor and let's look at the positive amplitude here. So note that positive amplitude here is 643 millivolt here, 643 here. Okay, and let's look at the negative amplitude here. All right, so let's do that here. So this is the negative part here. So the negative amplitude is almost like 800 millivolt here. So that's the output here. In red is the output that you see here, okay? Positive amplitude 643 and negative amplitude 800, which means that the sinusoid is distorted. A perfect sinusoid, we have applied a perfect sinusoid to the input. 10 millivolt positive magnitude, 10 millivolts negative magnitude, perfect sinusoid to the input here. The output is amplified. The output is obviously amplified. So if you look at 643 millivolt divided by 10 millivolts, so we have a gain of say 64 or so, but it's slightly distorted here. Positive amplitude and negative amplitudes are not the same. And that's because transistor is not a linear element. Transistor is a non-linear element. Specifically, the base emitter, when you look at the base emitter side here, you have a diode and the diode's current voltage relationship. So the way amplification is occurring is this voltage here that you see here, it goes to the diode here and it causes the base current to change here. But the relationship between base current and this voltage is non-linear because it's a diode. And then that base current causes a collector current to change here. The relationship between collector current and base current is linear, but the base current itself is non-linearly related to this input voltage here. And this collector current that you get here, the changes in collector current will cause a change in the output voltage here. That sinusoidal collector current would flow through a parallel combination of RC and RL, will cause a voltage here. So the relationship between the collector current and this voltage is non-linear. If I were to keep this voltage smaller, so instead of 10 millivolts, if you put 2 millivolts here, right? So we could do that. Let's say we put 2 millivolt here, right? Okay, so let's look at the output here. So input is 2 millivolt, perfect. Output is here. And you would see that the amplification nonlinearity is much less here. So output voltage is 142.2, positive amplitude. So let's look at the negative amplitude here. So let's look at here. Negative amplitude is 145.6. There will always be nonlinearity. Output will always be slightly distorted, but note that the distortion is much less. We have 142.2 and 145.6 here. So you have to apply very small voltages at the input of the amplifier on the bipolar transistor. Then only it will act like a reasonable amplifier. Otherwise, it will distort the signal here. All right. So that's something that we can observe and study with the help of the simulator here. All right. So what you could also do is, for example, you could take this voltage here and apply a fairly large voltage here. For example, let's say 25 millivolt here. Okay. You could apply 25 millivolt here, and the output now you will see is significantly distorted. Let's run the simulation here and see here. All right, so that you can see fairly distorted output here. And whether the distortion is significant or not, maybe what you can do is you can double click here. Right, so no, double click and scales and formats, save curves here. You could go here and you could look at you could try and hear the nature of the sound that is coming. So this is the input here, auto range here, and you could play and look at this. So this is like a pure 1 kilohertz sinusoid here. And then what you could do is you could go to the output side here and auto scale it here, and then you could play again and then see the effects of the distortion that the amplifier is doing here. And at this point, when you're applying a fairly large input voltage, you can clearly make out that the output is a distorted sinusoid. And distortion, what it results in is that in addition to 1 kilohertz input that you given, when a signal becomes nonlinear, you have other harmonics also. So if you listen carefully, you can listen to and see that the other harmonics are also present in the output here. So the simulator can allow you to explore all of these things in how an amplifier behaves. And I would suggest that use this to understand the amplifier better, all aspects of the amplifier. You can also look at what is the power dissipation here, what is the power dissipation in the transistor here, how much power is being delivered to the load. All of those things you can try and understand. How much power is taken from the source and how much power is delivered to the load here. All right, so all these things can be nicely explored depending on how much time you have. You could explore all those things here. So that's the amplifier part. The next thing is what we can do is we can make a inverter here. So in a digital circuit, the NOT gate is the simplest gate that we can have. And here is an example of a NOT gate. We took a transistor with a base resistor. We have connected input voltage here and taken a collector resistance and connected it here. And we can clearly see, first of all, we'll connect this later on. So when you do a dynamic DC, right? So we can see here that if you apply 0 volt, you get 5 volt at the output. The supply voltage is 5 volt here. So 0 and 5 volt here. Now let's change it to, so when you apply low, you get a high here. So let's change it to high value here, 5 volt here. And you get a low value here. 116.8 is a fairly low voltage here. And the magnitude of this low voltage you could control by changing the value of RC or changing the value of RB. So for example, if I make it 3K, I can reduce the value further, 98. Okay, so we can change all of that here. So that's, you can clearly see 0, low, high. And if you apply high voltage, you get a low voltage here, right? So you can do that and see. If you want to explore it further, what is the exact relationship between output and input characteristics? You could do that by running a DC simulation here. You could run a DC simulation and you can see how output changes. So what we're going to do is remove this here and connect it this part here. All right. So so let's do a DC simulation. So we are going to change now. The input was VI, right? So VI here, and I'm going to change it from, let's say, 5 to 0, and I'm going to look at the output voltage V0 here. Okay, so let's run it. Right, so this is the characteristics that you get here. This is the input versus output characteristics of a inverter here. So this is called the voltage transfer characteristics. Output voltage versus input voltage here. So this is the place where the transistor is off. The transistor is off, there's very little current flowing, and therefore the output voltage is practically equal to 5 volt here, right, this point. And you have to apply about 0.6 or 0.5 voltage here to turn on the transistor. Once the transistor turns on, a current starts flowing, and then the output voltage keeps on decreasing as you apply more and more current here. Once you apply a sufficiently large current, what happens is that the transistor goes into saturation. And once it goes into saturation, the voltage across the transistor becomes a fairly small value here. So this is the part where the transistor is in saturation. This is the part where the transistor is in cutoff. And this is the part where the transistor is in active mode here. So you can see all of that, study all of that. And you can explore, for example, if I put instead of 2K here, if I put 1K here, well, 1K is not enough to saturate the transistor, that you don't see that characteristics here. So right, so we need to put it 2 volt here. Okay, I could increase the value here. Instead of 390, maybe 490 here. All right, so all of those things that one can explore with this here. So it acts like a inverter, this one. And so let's come out of here. The other thing that one can do is one can do a transient simulation. So one can apply a step here. If one applies a step here, say you go from 0 to 5 volt, then this will of course go from 5 to 0. But it will not go from 5 to 0 abruptly. You will see that there is a delay that is there here, because the transistor has internal capacitances. And they have to be charged and discharged, and that's where you see the delay occurring here. So we could do a transient simulation. So for transient simulation, note that I'm applying, this is the transient part, I'm applying 0 to 5, and rise time of my input I've kept small, 0.1 microsecond, 0.1 microsecond, applied a pulse width of 20, and period of 40, okay? And let's do transient simulation here. So we're going to look at the output. So let's switch off all of these things here. That was for the different circuit here. And we are looking at these two, input and output, right? And note that we have applied a fairly, this thing. So I'm going to simulate it for, let's say 100 microseconds. And I'm going to increase my resolution here. And let's see what happens here. Okay, so in blue we have the input. Input is going from 0 to 5. And in red is the output voltage here. So when I go from 5 to 0, I expect my output to go from 0 to 5. It does go from 0, very close to 0, to 5 here, right? From low to high. But it takes a certain amount of time to go there, right? And that's where you are seeing that there's a delay. All logic circuits, NOT gates, AND gates, OR gates, all of them have delays. And those delays are coming because of internal transistor capacitances. So typically we define delay as the time, you take from a place where you have 50% of the input. So input is 5, so you take a 2.5 volt, and you see how much time does it take for the output to go to 50% of the total voltage here, so 2.5. So you take the outputs 2.5 and inputs 2.5, and you look at the difference between those two, and that would tell you the delay here. And similarly, when you go from 0 to 5, the output goes from 5 to 0, and again there is a delay here. There's a delay here, right? So all these circuits will have delays. And note that if I try to switch very fast, then my input will not be able to follow. So you could study that as well if you try to switch it very fast here. Let's say I try to switch at a higher frequency. So reduce to 2 microsecond and reduce it to 4 microsecond, right? So let's do that. And we have to reduce the simulation transient limits. So instead of looking at this thing, let's look at 10. Note that our inverter is not working properly, right? So the inverter is failing. I switched from 5 to 0 and 0 to 5, but look at the way the inverter is not able to respond, right? So that brings an important point that all of the inverters, all of the logic gates, there is an upper limit of frequency at which they will operate properly. And that limit is eventually decided by the transistor capacitances, because the capacitances have to be charged and discharged. So when you switch, if you don't give them enough time, the capacitor will not be able to charge and discharge. So for example, if let's say the node is at 5 volt, and when you switch from 0 to 5, this has to go from 5 to 0, but there's a capacitance that has to be discharged. And if you don't give enough time, it may only go from 5 to 4 volt and is still high. And therefore you didn't give it enough time to go to 0, and therefore it didn't go to logic 0 here. So all of these circuits will fail beyond a certain frequency. And that is all happening because of the internal transistor capacitances. And internal transistor capacitances and these resistors play a role, right? Because there's always a charging or discharging time constant. So along with capacitors, the resistors play an important role here. So what is the, this resistor would be charging up the base emitter capacitance. This resistor would be charging up the capacitances that you see here. So all of those things play a role in determining the speed of the inverter here. The next thing that you could do is, for example, once you have an inverter, you could take two such elements here. So this is one and this is the other one. And you could connect them in parallel and you can create a NOR gate here, right? So two inputs are there. Let's call this VA here. So this is input A. Sorry, so I guess I have defined A somewhere else also. Let's call it VA1. All right. So there's an input VA1 and there's an input VB here, right? And this is the output here. And so this is what we are saying is that this is a two input NOR gate here. So when both of them are high, when this is 5 and this is 5, the output voltage, you can use dynamic DC to explore it. All right, dynamic DC here. So both of them are high, 5 and 5 here. The output is 87 low. So that's fine. One of them, let's say I put to low. Well, still is low. The value of the voltage changes a little bit, but logically it is still low, right? So when this is 0, this is still high, low here because this value is high here. So that's the behavior of the NOR gate, right? A NOR gate means that when both the inputs are high, then only you will, when both the inputs are low, then only you will get a high. If even one of the input is high, then you will always get a low, right? So that's the behavior of the NOR gate. Now let's put both of them low, right? So both of them are low here. Now it goes to the high value here, 5 volt here. But if one of them is high, it will be low here, right? So by connecting two of them, we have constructed a NOR gate. Now I would like you to think how you can construct a NAND gate here. And so these are the basic building blocks of all digital circuits: the inverter, the NOR gate, and the NAND gate. And once you can construct an inverter and a NOR gate and a NAND gate, you can interconnect them and you can do a adder, subtractor, multiplier, all of those things, and it eventually leads us to a microprocessor. You can construct a processor and a computer using these basic elements that you see here, right? So these are at the heart of, in the next lab, we will see instead of a bipolar transistor, we'll use a MOSFET. Which is used in most of the circuits. So we'll use that to construct a inverter and a NOR gate with that. All right, so there's plenty to explore, starting from the BJT characteristics to the BJT amplifier that you see here, then an inverter, then a NOR gate, and you could explore also the NAND gate that is there here. When a quiz is held, the quiz would not be would be based on something simpler, maybe a BJT amplifier. We will not ask you to make a NOR gate or a NAND gate and all that. We'll do something simple there in the quiz as far as the quiz and all that is concerned. So beyond quizzes, what this tool and simulation in this lab is offering is that many of these things that you studied in theory, you can explore them in a lot more detail. And in a more convenient manner. You can easily change things and see what the impact are, and it gives you an opportunity to explore and play with the ideas. All right, so fine. So let's stop here.